Let's do example number 9. This one looks quite a bit different. This time we have an object that's on an incline. We call it an inclined plane. Really what it is a hill. But in physics, we tend to like to give things more complicated names. Maybe it makes us sound smart or something if we call it an inclined plane rather than a hill. But that's what it is. It's a hill. Now, on this hill, you can see that we have, well, there's only labeled one force, the force of friction, and it's acting up the hill. Why do you think friction is acting up the hill in this case? Yeah. Kind of. It's going to move down the hill, right? It's going to move down the hill. But it's not just gravity pulling it down the hill. If it was just gravity, which way would it go? If it was just gravity, it would go straight down. And it doesn't go straight down. It goes down the hill, parallel to the hill. Yep. The mass, yeah, the mass, what do you mean there? Like, is it because the mass as well? Yeah, yeah. So part of it is gravity, and part of it is the incline itself that causes it to move not straight down. Let's draw a couple more forces that are acting on this. Okay. We know that there has to be a force pulling it down the hill, and that force has to be parallel to the hill. We're going to actually call that F parallel. The symbol for that is going to be F parallel. But that F parallel comes from something else. It's not a force in its own. If you were to look at the fundamental forces that are acting on this object, you wouldn't see F parallel. F parallel results from a couple of other things. Firstly, there's a force of gravity acting down. So let's draw that. Force of gravity acting down is m times g. In this case, it would be 2 times 9.81. Now, there's another force acting on this as well, and that's going to be the normal force. But the normal force pushes at 90 degrees. I can draw that normal force wherever I want. I'm going to choose to draw it right here. Make sure that when you draw that normal force right here, Fn, make sure that you draw it perpendicular to the surface. I have it drawn perpendicular to the surface there, right? And make sure you don't draw it too long. How long is too long? This is too long. How do I know that? Because the combined normal force and gravity, if I add these two vectors together vectorially, right, and we know how to add vectors together, the sum of those vectors, the combined vector there, the resultant vector, has to be parallel to the hill. I'm going to call this F parallel. Fn and Fg is F parallel. Now, I'm going to redraw it up here. So F parallel isn't a force on its own. The force that pulls it down the hill, that friction in this case counters, is really just a combination of the normal force and the force of gravity. Now, we need an angle in this triangle. Here's the good news. If this angle is 30 degrees, and this is 90, and it will be, because gravity always acts straight down toward the center of the Earth, then this would be 60 right here. And this is 90, so this angle right here would be 30. This angle right here is always going to be the same as this angle right here, always. You can do the geometry with it and see that, but in the end, it's always going to be the same value. If it's a 30-degree incline, it's going to be 30 degrees between the normal force and the force of gravity. Now, what we need here is the value of F parallel. Before we do anything else, we need the value of F parallel. So let's get it. Let's say sine 30 degrees is equal to opposite, which is F parallel, over hypotenuse, which is the force of gravity. So I'm going to say F parallel is equal to mg sine theta, or 2 times 9.81 times sine 30 degrees, which ends up giving us 9.81 newtons. So I got confused there for a second. I thought we had a mistake in this. We had a mistake in the way that I was reading the question to you, but not with the question itself. This force right here is not a force of friction. It's just a force. How did I catch that there was something wrong going on here? When I got a value for F parallel of 9.81, how did I realize that something, either with the question or the way I was reading the question, was wrong? Yeah, yeah. Friction's not going to be higher than F parallel, right? Friction, if that was friction, it would have to be lower than 9.81. This F over there, this 20 newtons, this is just somebody pulling it, some guy pulling it up the hill. It counters this F parallel of 9.81 meters per second squared. Now, what do you think I'm going to do next? Yeah. Yeah, let's straighten it out. Let's do what we always do. Let's say, here's our object here. It's 2.0 kilograms. We got a force. I'm going to call it F1. That's the guy pulling. It's 20 newtons. And I'm going to call this F parallel. And the value of F parallel is 9.81 newtons. And then I'm going to say F net is equal to the sum of the forces. F net is equal to F parallel plus F1. F net is mass times acceleration. This is step 3. F parallel plus F1. And then mass is 2 kilograms. A is what we're looking for here. F parallel, we just figured out a minute ago, was negative 9.81. Negative because it's to the left in my diagram. And F1 is 20 newtons. Solve for A. 20 minus 9.81 is 10.19. 10.19 divided by 2. Sorry. 10.19 divided by 2 would be 5.1 meters per second squared. So it would accelerate up the hill, okay, positive direction, of 5.1 meters per second squared. Okay, there's no problem with this, right? Once we get to this point, we're good to go. The problem is getting to this point. We need to find F parallel, which remember is the combination of the normal force and gravity. Why did we not include in this run right here? Why did we not include Fg and Fn? Why did we not include Fg and Fn? Yes, we did include Fg and Fn, right? We did. It just doesn't look like it. We included Fg and Fn right here. F parallel is Fg and Fn. Fg and Fn don't cancel each other out like they do in most of the questions that we do. Not at all. We have to include Fg and Fn, but we are including Fg and Fn when we did our little vector analysis here to find F parallel. That make sense? So make sure when you draw this diagram here to get F parallel, make sure you draw it right. Fg has to point straight down. Fn has to point at 90 degrees to the surface. 90 degrees to the surface, right? And make sure that Fn is 90 degrees to the surface, and make sure it's not too long. The sum of those forces, the combined force, their F parallel, has to be drawn parallel to the surface. It should be drawn parallel to the surface. If you don't draw it parallel to the surface, you're going to end up using the wrong trig function to find its value. Okay, look, if I draw it like this, F parallel like this, you're going to end up using a different trig function to find the value of F parallel. It's going to be wrong. Does that make sense? All right, I'm going to set you free on some questions in a moment, but before I do, I want you guys to just do one small thing. I want you to find F parallel for this 20 kilogram object. Okay, draw the diagram, draw it out like we did, find the value of F parallel. Don't worry about going any further, okay? Just find F parallel for this object. Okay, this is not part of a larger question right now. The larger questions where we want to find the acceleration on your worksheet that you're going to do after we've mastered finding F parallel. The angle is going to be 30 degrees. All right, let's have a look at this. We have, if we want to find the F parallel for this, we have we have gravity acting down. That's going to be m times g. We have a normal force acting perpendicular to the surface. It's going to look like this. Now make sure you draw it the right length. The normal force does not go all the way down here. That way, if it did, then we would say F parallel is not actually parallel. That doesn't work. F parallel needs to be parallel to the surface. So we have to stop drawing the normal force right there. The sum of the vectors, the one that I'm drawing as my dotted line vector here, is F parallel. And that's the same vector as this one right here. There's not two F parallels. I'm just drawing it twice. two different places. Now, what's the angle up here? Always going to be the same angle as the angle of the hill, right? So it's going to be 30 degrees in this case. We know that's 30. This is 90. This must be 60. And if that's 60, this must be 30. So it is 30 degrees, and it always will be. We want to find F parallel. It's the opposite side of the triangle. We have the hypotenuse, mg. So we're going to say sine 30 degrees is equal to opposite F parallel over the hypotenuse, m times g. So we're going to say F parallel equals mg sine 30, which is 20 times 9.81 times sine 30, which ends up being 98.1 newtons. How many people got that? Good. So once you have F parallel, guys, this turns into a question like any other, right? The difference between this question and the others is this. It's kind of like step 1.5, right? Remember when we had those wagon problems where we were pulling it up at an angle? It was moving horizontally, right? Okay, remember we had those? There was 4 steps, but we had to add a step 1.5 in there, right? Same kind of deal right here. Okay, if you want to do it kind of off to the side, if you want, for step 1.5 to find F parallel, and then just treat it like any other question. All right, what I'd like you to work on now and for the remainder of class, the next 20-ish minutes, 23 minutes or so, is worksheet number 12, questions 10 to 14.